Hi and welcome everyone. In this video, I want to go over the effects of elementary row operations on determinants. So let's see what the effects are. And of course, we're going to try to prove them. Now, the first one is multiplying a row by a constant. So if you have a matrix, you multiply a row by a constant, that's alpha. You get a matrix B. So the determinant of A becomes 1 over alpha times the determinant of B, or and the determinant of B is going to be just alpha times the determinant of A. The second one, if when you interchange two rows or you permute two rows, then from A you get the matrix B, then the determinant of A equals to minus the determinant of B, or the equals to minus the determinant of A. Next one, when you multiply a row by alpha and add it to another row, so row J, and then you change row J, then the determinant does not change. So let's see how this works. The first one, multiplying a constant by a row, so row I. So this is, we get alpha times the determinant of A equals to the determinant of B, or the determinant of A is 1 over alpha determinant of B. Now let's see the proof of that. So let's say we have the matrix A, and I just picked the ith row of that matrix, and you multiply that by alpha, so you get alpha times A11, AI1 times alpha times AI2 and times dot 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 alpha times AIN. Now the formula for determinants, so please watch that lecture on determinants. We know it's going to be sum of, when we do ith row expansion, A sub ik times C sub ik, and the k going from 1 to, and that's the ith row expansion. Now if you want to write the determinant of B, it's along this row is just going to be alpha times ik, A sub ik, C sub ik, and as you know, we can take alpha out here, so this is the same thing as alpha times that, so it's going to be the determinant of B equals to alpha times the determinant of A. So the proof of this is pretty straightforward. Now I'm going to talk about C in the next proof, so probably you should know by now what C is, but we're going to talk about that. The second one, it says when you interchange two rows, you permute two rows, and you go from A, you interchange or permute row I and row J, and you get the matrix B, and the determinant of A equals to the negative determinant of B. Let's show this one by induction, or let's prove it by induction. So as you remember the steps for proving by induction, the first step is show it's true for n equal to 1, to 2 in this case. So if you take a 2 by 2 matrix A, B, C, D, we know that the determinant of A is going to be A times D minus B times C, so that's what we get. Now if you permute row 1 and row 2, we get the matrix B, which will be CD AB, and the determinant of B is going to be C times B minus A times D, and that's minus the determinant of A. Now part 2, so it works. For n 2 by 2 matrix, we got it. In part 2, we suppose that it's true for k minus 1 by k minus 1. You can even put n minus 1 and minus 1 here, it doesn't matter. So it's true for that. That means let's take a matrix that is k minus 1 by k minus 1 and permute two rows, and you get the matrix B, and we suppose that the determinant of D equals to negative the determinant of E, or the determinant of E is negative the determinant of D. So this is, we suppose this is true. See how it's going to work for an n by n matrix or k by k matrix. It doesn't make any difference. You can just pick any of them. So let's say we have a matrix, and I'm going to put n by m here. So we have an n by n matrix F. We permute two rows and we get a matrix G, which is also n by n. We want to show that the determinant of F is negative the determinant of G. Now we can find the determinant of F by expanding along a row other than row I and J. So we can pick a row K. So, and I wrote that here. Let's say we have an n by n matrix here. And what we can put is, this is row I, this is row J, and this is row K. So we interchange row I and row J. So again, that becomes this row. So it's, we interchange these two rows. So we get AJ1, AJ2, dot, 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 AJN. And here we have AI1, AI2, dot, 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 AIN. Okay. Then we are going to find the determinant by k-row expansion. That means along this row. So the way you can write that, you can say the determinant of F equals to the sum of kr, a sub kr, and I put here C1 kr, and I used r in this case. You can use any variable you want, r going from 1 to n. So this is k-row expansion for the determinant of F. Then you can do k-row expansion for the determinant of G, same way. You can write AKR, A sub KR times C sub KR, but C2, let's call that C2. But what is C1 KR? That's negative 1 to the power of K plus 1 times M1 KR, and C2 KR is negative 1 to the power of K plus 1, K plus R M2 KR. Now, what are M1 and M2s? M1 and M2s are both the determinant for n minus 1 by n minus 1 matrices like D and E in part 2. In part 2, and I brought that here. We know when we suppose that this is true, when we have n minus 1, or k minus 1 matrices, when you interchange the row, you suppose that the sign of the determinant changed. Now, for that, we can write that M2KR equals to negative 1 M1KR. Therefore, C2KR becomes negative 1 C1KR. And when we write the determinants again, so the determinant of G is going to be AKR times C2KR, and then the sum going from 1 to n, and that equals to the sum going from 1, again, R going from 1 to n, A sub KR minus C sub KR1, and you can take the negative out, and guess what? That's just it's negative the determinant of F. So if we check here. Now let's go over the third one. When you multiply a row by a constant and you add it to another row and change row J, the determinants don't change. We can do this by using induction also. So we have to show it's true for n equals to 2. So if you write a 2 by 2 matrix, you can use A, B, C, D, or for this one, I used A1, 1, A1, 2, A2, 1, A2, 2. The determinant of A is the product of these two minus the product of these two entries. So that's what we get. Now, if I do alpha R1 plus R2 and I change R2, we get R2 becomes alpha A11 plus A21 and alpha A12 plus A22. And that's our matrix B. Let's find the determinant of B. The determinant of B is that times that minus that times that. And I wrote it here. And as if you expand this, these two cancel, and at the end you're left just with that expression, and that's just the determinant of A. So it's true for n equals to 2. Now we can suppose that's true for all n-1 and by n-1 matrices. That means if you have a matrix C, it's n-1 by n-1, and you multiply a row by a constant, add it to another row, and change the second row, you get the matrix D. So we suppose that the determinant of C is the same as the determinant of D. Now we need to show in part 3 that is true for an n by n matrix. Let's take a matrix G n by n, and we're gonna multiply a row by a constant added to row J, and row J changes, and we get another matrix which is still n by n. Let's call that F. Now finding the determinants of G and F by K-row expansion. So we can write the determinant of G sum of R going from 1 to n A sub KR, and again I call that C1 KR, and the determinant of F, same thing, but you can write C2 KR. Now we want to see the relation between these two. Now C1 KR is -1 to the power of K plus 1 times M1 KR, and C2 KR is -1 to the power of K plus 1 times M2 KR. And from part 2, just like we saw in the second example, the second proof, these two are the same. Therefore, we can say that C1 KR is the same as C2 KR. And if you write the determinants, again, the determinant of F is sum of R starting from 1 to n A1 A sub KR times C2 sub KR, but you can just write this as sum R starting from 1 to n A sub KR C1 KR, which is the determinant of G. Therefore, the determinants will be equal. You can also prove all these 3 row operations, the effects of those row operations, by using elementary matrices, and I think I did that in the sample exam. So both ways are okay, but make sure to know both of them. Using elementary matrices, it's probably shorter, and using induction. Thank you for watching, and I'll see you in my next video.